All right, so today we're going to start on new material and start talking about cluster analysis. So cluster analysis is another exploratory technique. Principal components we talked about as being kind of an exploratory technique where we're looking for pictures and summary statistics that we can learn from about our multivariate data set. Clustering is a similar idea, it just in the sense that we're trying to find structure in the data. And specifically, we're trying to find how do the individuals or maybe the variables group together, or both. So remember, we have N by P data matrix, individuals in the rows and variables in the columns. And we could ask, if we were looking for, what structure is there in our data, we could ask that in a couple of ways. One way to ask that would be among the individuals, the rows, are there groupings, natural groupings, where they look similar there. That's like asking, can we cluster the individuals or the rows? We might also be interested in clustering the columns, which would be the variables. Do the variables that I'm measuring group together in some sensible way? Okay, and then the whole exercise of clustering is driven by how do you want to define how close one thing is to another thing. So distance is a big consideration when you were talking about cluster analysis. We have to define a way to call one item more or less similar to another item as compared to others. So first, let's be specific about what we mean by closeness, similarity, distance, that kind of thing. So maybe the simplest way to define distance between any two items, whether they're individuals or variables, would be a Euclidean distance. So what we have on the screen there, or a statistical distance, which is basically the Euclidean, where we include this weighting by something, capital A, often an inverse of a covariance. But there's different ways to define distance. So there's lots of different choices for calling one vector of numbers similar to another vector of numbers. Those would probably be the first two that come to mind. Here's a couple of others. Something called the Minkowski metric, Canberra metric. And these all have slightly different interpretations of what how they're defining distance. Most of the time, it will be Euclidean / statistical distance that you work with in practice, or, like we'll see momentarily, correlations. So the authors point out a couple of times that, like here, when clustering individuals or items, that would be the rows, often that's done with a distance, like a real distance calculation, like a Euclidean distance or something. And whenever variables are grouped together, it is often on the basis of a different way of representing similarity, and that's just correlation coefficients. So you can do it either way. You can treat a correlation matrix basically like a distance matrix. If we say Euclidean distance is how I'm going to define how similar items are and do this cluster analysis that we're about to learn more about, then you can compute them that way, or with the correlations, you can represent distances as, say, not positively correlated. Like, how uncorrelated are you? I'll show you an example in a minute. Distances, there's different types of distances. Also, there are ways to talk about distance when you have categorical variables. So we're talking about two numerical vectors that I could compute a Euclidean distance on, say. But what if I have binary variables? Yes or no, presence or absence, dead or alive type things. You can still do this cluster analysis, but again, you have to think about what do you mean by similarity or distance. And there's a few slides, more detail than definitely you need, for sensible ways to do it with binary data. I'm going to go through this quickly. I should say there's 120 slides on cluster analysis, but I'm going to try to cover cluster analysis in 3 lectures. So we're going to be picking and choosing out of the slides what I think is the most important parts. This is all still about categorical variables. I'm going to go here. That's still categorical variables. Okay, so just looking at the bottom comment there, many different ways to define similarity. Could be an actual distance, like a Euclidean distance or a statistical distance. Could be something else that we customize, but that somehow represents what we believe is important for closeness. Could be correlations, for example. I'll show you exactly how to do that momentarily. Here's a data set that we're going to mention a couple of times. Just wanted to introduce it. This is data on these different languages and trying to find concordance between the languages. So the idea is, what is your word in this particular language for the number 1? And what is your word for the number 2, 3, ... And let's compare these languages in terms of the first letter for those words. Like, is my word for the number 1, does it start with the same letter as that person's word for the letter 1 with a different language? The data look like this. So we have for 11 different languages, English, Norwegian, Danish, and so on, going across the columns. We have the words for the first 10 integers in those languages, and we can turn that into data, like a distance matrix or similarity matrix, like follows. So here's a table that shows cross tabulations. First row, first column, that's E row with E column. That's the number of words, 1, 2, 3, 4, ... up to 10, in the English language that start with the same letter, whose corresponding words start with the same letter, also in the English language. The number is 10 because English to English matched every time. Second row, first column is in compared to E. What is in? Norwegian. Norwegian compared to English. And so 8 of those words started with the same letter. So that's a P by P matrix of numbers. They're not really distances, but in some sense they're informative for assessing similarity. We might use these like a distance. We'll see those data in just a second. Okay, so the different ways to do this idea of clustering. Basically, we're going to be comparing items, either individuals, rows in my data set, or variables, columns in my data set, and asking about who's most similar to who. Let's group individuals or items or variables into clusters within which they are more similar to each other than to everybody else. Have to define what we mean by distance. So we've just addressed that. There's different ways to define distance. And then you have to decide what kind of method or algorithm do you want to use to do the clustering exercise, because there's no perfect answer for clustering. We have p variables and n individuals, and it's a kind of an open-ended question. How do you group? What's the best grouping of the data? So there's different ways to do it, and one of them that I hope to spend the rest of today's lecture on is hierarchical clustering. This is probably the first exposure that you would have to the idea of clustering, is hierarchical clustering. So let's spend a little time with it. Let's go here. In the most widely used type of hierarchical clustering, which is called agglomerative, it's an algorithm. There is no formula for the cluster equals such and such. It's an algorithm. Well, I guess there is, probably, if you worked hard enough. But here's how it works. So every individual is first considered as its own, quote, cluster. Let's suppose we are clustering the individuals, the rows of our data set. So I'm going to say individuals. Slides say items. We mean the same thing. Every individual is its own cluster to start. And we could compute a distance matrix comparing all those, quote, clusters amongst themselves. Call it capital D. So that would be what we started with on the previous slides, talking about like a matrix of Euclidean distances, a matrix of correlations, things like that. So the start of the algorithm we treat like every individual is its own cluster, and so the distance matrix is the original one. Okay, then we look within the distance matrix, zeros on the diagonal, and then numbers that, if they are smaller, indicate greater similarity between pairs. And if they're bigger, represent poorer match. So we search the distance matrix for the smallest distance, the one with the nearest, most similar pair of clusters. And let's say that out of our capital D, or out of our N individuals, U and V correspond to that smallest distance. Then we merge U and V. So step one of the algorithm was to go find which pair is most similar out of all pairs. Pick those up, put them together. They are now a, quote, cluster. Everybody else is still their own cluster, but now we have this new cluster composed of two individuals. And then you iterate and treat it as if that new cluster, or you have to recompute the distance calculations now, because these two entries, these two individuals, U and V, are no longer in there. They're together. So now you have to think about what's the distance between UV and any other individual. What's the distance between this individual one quote cluster that has one individual in it and this new cluster that has U and V in it? There's choices for how to do that. We'll talk about how to do that in a second. But once we have decided how to actually calculate that distance, we have to compute this distance matrix that's specific to this new cluster that we've created. So we have a new distance matrix. If we had n objects to begin, we now have an n minus 1 by n minus 1 distance matrix. And then we do the same thing. We search that one for the smallest entry and join. Recompute distances, do it again, do it again, do it again. And you get, let me just show you what one looks like. You get a picture like this from hierarchical clustering, where let's say we had 5 items. I'll talk about this example in a second. If we have 5 items, we see a pictorial representation of items 3 and 5 being most similar because they were joined initially. And then beyond that, item 1 was most similar to them. And then these were kind of similar. And then finally, this was the biggest distinction was between those last 2 groups. So that's where we're going with hierarchical clustering. There's several different ways to do hierarchical clustering, but at the end of the day, you end up looking at one of those pictures that I was just showing. So let's think about that task of comparing this cluster UV with any other individual. There's 3 common ways to proceed there. How do you define distance between one individual and a cluster containing 2 individuals? There's 3 common choices. They're called, and it's referred to as the linkage, the choice of linkage in your clustering routine. They are called single linkage, complete linkage, and average linkage. And so on the screen is a simple example where there are 5 items. There's currently 2 clusters. The first one contains items 1 and 2, and the second one contains everybody else, 3, 4, and 5. The distance between these 2 clusters requires that we define what we mean by that. We have to say what we want for the quote linkage. And if we say linkage is single linkage, that's the first row here, then the distance between the 2 clusters is basically as small as it can be. So we'll define it in just a second, but the definition of single linkage distance between those 2 clusters is the minimum pairwise distance. I'll show you that in a second. Versus complete linkage, where it's the maximum pairwise distance, it treats them as if it's harder to bring things together. And then average linkage, which is an average of all the pairwise distances. End of the day, it's all hierarchical clustering. We're just picking among 3 choices of how to define intercluster distances. Okay. So single linkage is kind of spelled out in more detail here. If we have that cluster UV, and then we consider any other cluster, it might be one individual. Let's say it's one individual. So here we are with everybody's still their own cluster except for U and V. They started their own. The distance between UV and W is defined to be the minimum pairwise distance. So you take the distance between U and W and the distance between V and W, and the smaller one is what you call the distance between UV and W. So U could be very close to W, and V could be very close to W, in which case the distance is like supported by both of them. But if W is very far away from V, for example, but really close to U, you're still going to call UV close to W, if that's your choice. So it kind of makes it as easy as possible to find attractions or similarities between clusters. This is worth seeing. So let's see this example of a toy example where we have the distances provided to us. So we had some data set with 5 items, and we computed a distance matrix for those 5 items. We don't know what these are. These are just hypothetical distances. They could be Euclidean or whatever. As far as clustering goes, hierarchical clustering, all it cares about is the distance matrix. First thing it needs is the distance matrix. Okay, so let's just kind of walk through what it would look like, hierarchical clustering with single linkage, and the distances are right here. Step 1 would be to find out of that distance matrix the smallest number, which is 2. There will be zeros on the diagonals because those are just distances between one thing and itself. So 2 corresponds to item 3 and item 5. If we said D53 was matrix D, 5th row, 3rd column, that's the number we're talking about. That's 2. So we would merge those 2 objects, 3 and 5. 3, 5 is now a cluster. And now we have to update the distance matrix because it's not 5 items anymore. It's 3 individual items in one cluster of 2. So we have to, like in that matrix, we're about to compute this matrix right here. Some of these distances are unchanged. The distance between item 1 and item 2 is 9. Distance between item 1 and 2 is 9. So that we're not doing anything to those. What's changing is, or what I have to be specific about is what are the distances that involve this new cluster that we just created. So that's what we're computing here. The distance between 3, 5 and 1 is the minimum of the pairwise distances. So what's the distance between 3 and 1, and what's the distance between 5 and 1? Take the smaller of the 2 and call that our distance. So this 3, 7, and 8 is what went in the first column of this new distance matrix. Then we repeat. Where's the smallest distance? And it's first row, first column, which corresponds to item 1 and the cluster 3, 5. So now we are going to merge 1 into that cluster so that we have a cluster 1, 3, 5 now. And we redo the whole process. So now we get a new distance matrix. We do it again and again, and we wind up with a representation like this. So this is called a dendrogram, tree-based representation of a hierarchical clustering analysis. And what it tells us is 3 and 5, items 3 and 5, were the first to be merged because their distance, this merged distance right here, was 2. The distance between 3 and 5 was 2. So that was the smallest. They were joined together, step 1. Step 2 was to group 1 in with 3 and 2, or 3 and 5. So this join event happened, and the distance involved in that join event, so the distance between item 1 and the cluster 3, 5, was 3. So that's the 3 right there. And then you can keep going. After that, once those 3 are together, the next nearest pair of items was the 2 individuals, 2 and 4. And at the end, the only thing left to do was put them all together. Okay, so why would we want a picture like that? What use is it? We've just taken our multivariate data and turned it into a picture. And so hopefully we can look at the picture and learn something about structure in the data. I'll show you an example of doing that. Here is the language data again, 11 languages, and we had those counts of concordance on the first letter of the words 1 through 10. And we have turned those counts into a, quote, distance matrix. It's not really a distance matrix. These aren't Euclidean distances or anything, but they are now numbers for which smaller values indicate greater similarity. Like English and Norwegian, the number is 2, but they actually had 8 out of the 10 words that shared the first letter. Whereas English versus Italian is 6, there was more discrepancy. So bigger numbers indicate less similarity. Call it a, quote, distance matrix. So this is an example of doing hierarchical clustering with single linkage on these distances. Okay. It's an interesting example. We'll just go through it in a little bit of detail. These are our distances. So step 1 is to search it for the smallest numbers. And there's actually 3 occurrences of the same smallest number, which is 1. And so what do you do when that happens? Do you put them all 3 together? No, you wouldn't do that. Do you make that joint right now, and that joint right now, and that joint right now? So if you think about what would happen if you answered yes to that, 2 of those tight matches, the 2 tight matches correspond to Italian and French, and Italian and Spanish. So suppose we said we're going to put Italian and French together, call that a, quote, cluster. But now what about Spanish? I wanted to put Spanish together with Italian also and call that a cluster. They were both as close to Italian as each other. What about putting French and Spanish together with Italian at the same time? The algorithm won't do that because Spanish is further away from French than it is from Italian. So it's kind of a subtle point, but it just illustrates some of the kind of detail that has to go into the algorithm behind the scenes for us to come up with a, quote, cluster. So just remember that somebody has made decisions about tricky questions in the code somewhere. In this example, here's what ends up happening, and I'll show you the code momentarily. We get a dendrogram that looks like this. This is for the language data, single linkage with those custom distance measurements. And what happened was, let's go do this in R, and we'll talk through the dendrogram there. So in R, the script is on eCampus. Let me remind myself what the table number is. 12-3. So I'm going to get script for 12-3. Okay. So this is the data for the counts of concordance for the languages. Let's load them in. Right. So it's a symmetric matrix, 10 down the diagonal for perfect matches between the same language, and otherwise they are concordance measurements between languages. In the notes, we turned those concordances into, quote, distances, and the way we did it was actually just to subtract 10, or to subtract them all from 10. So let's do that. Now the matrix is that, zeros on the diagonals, and small numbers correspond to greater concordance, greater similarity. So that is a sensible distance matrix. Okay, and then how do you do cluster analysis? Because you don't want to have to do what we did in the notes manually, obviously. You don't want to have to code that up. So R has functions for doing lots of different types of clustering. For hierarchical clustering, there's a function called hclust. And hclust needs, all really it cares about is the matrix of distances. So you just need to provide it with, first and foremost, distances. So I took our matrix of numbers that we're calling distances, and I wrapped it in this function called as.dist because R has a special class for a distance matrix. There's a function dist, question mark dist, which if you were to give it like an n by p matrix would estimate or would compute a distance matrix. And then it's represented as this is a distance matrix to R. It has a special class. And I think hclust wants its input to be of that class. That's why I have as.dist. hclust D is a distance matrix as produced by dist. So in order to make hclust happy, I did as.dist of our matrix. Otherwise used default measures. And again, if we look at the help file for hclust, there are choices that have to be made if we're going to do this hierarchical clustering. One of them, or I guess the key one, is having already made a decision about what distance means. The key one is, what do you mean by linkage? By default, hclust assumes you want complete linkage. So if you don't say anything, it's going to do complete linkage, but you can choose from several others, including single linkage and average linkage. Those are the most widely used. If I had to pick one, I would pick average linkage. I think you can find examples where one will do something interesting relative to the others, but there's not a perfect reason to generally pick one over the other. So I would tend to pick average linkage. Okay, so I am about to call hclust, and let's do that and see what happens. If you just say hclust, nothing really happens. It didn't make a picture. It didn't print out much of interest. There is some interesting stuff in there, so let's hang on to that stuff. I'm going to assign the output to an object. Here's some of the things that are available. There is, in the merge item, a summary of what happened as the tree was constructed. So this information would allow you to reproduce the tree basically from hand. What it means is, and you could look at the help file for hclust and it would talk you through it too, but what it means is the first event joined items 2 and 3. -2, -3 means individual 2, individual 3. As opposed to if there's a number without a minus sign, that's going to be something that's a cluster that was been defined up above. So I'll just talk through 3 of these rows. This says that the first merge event was individual 2 and individual 3. The second merge event was individual 6 with individual 8. The third merge event was individual 1 put together with the cluster that was defined in step 1. So if you ever want to try to recreate one of these pictures or really understand what it's doing, you can look here. Also available is the merge heights. So those correspond to where vertically the joints are in the little tree diagram, the dendrogram. But really the first thing you want to, I guess the main thing you want to see after you do clustering is the picture. And I can say plot on the output of hclust. There's a method for plot that applies to hclust type objects. And it looks like this. Okay. So what it's saying, I guess, first of all, what does it say in like the broadest sense? Why would you make one of these pictures, and what do you do with it? You're really kind of interested in, are there parts of the picture that look distinct from other parts of the picture? You're trying to group individuals or items. So you might look at a picture like this one and say, for example, these 4 languages appear to be pretty different from all of these languages. Within these languages, these 3 look to be kind of distinct. Overall, maybe I'm comfortable saying there's 2 real high-level differences or clusters. There's this one over on the left side of the picture, and there's that one over on the right side of the picture. Or should I say there's 1, 2, 3, 4 clusters that are meaningful. So you make a dendrogram like this, and you have to make a decision about like what you want to do with it. What level of detail do you want to focus on? We'll talk about how to make decisions about, like, should I call this 2 clusters or 4 clusters? because it has different interpretations. You know, it tells you a lot different stories if you answer differently, or just more detailed stories, I guess. Okay, so what happened in the algorithm itself? We have not a whole lot of time. So let's see. I'm going to show you how you can change the linkage real quick. In hclust, question mark hclust. If we wanted to do complete linkage, it'd be very easy. We could just type method equal complete, or method equal to average, or method equal to single. But I think I need to keep moving for now. So let me go back to the slides and just say, here's the picture for single linkage. Complete linkage is the same algorithm. It's just that we define inter-cluster distances differently. They're now the maximum pairwise distances. And it results in a slightly different, result from the algorithm because some of the calculations are different. And which one of these to choose? Should it be single or complete or average linkage? Read through the examples. There are some subtle differences in the kind of the stories that the pictures tell depending on the linkage type. But I did want to show you this example here, which is a little bit different. It is data on 22 U.S. public utility companies on 8 variables. And there's details on the variables, but for us it's just x1, x2, ... x8 for 22 companies. So let's, quote, do cluster analysis. Well, one initial question to answer is, what do we want to cluster? What are we interested in searching for relationships in? We could cluster the companies. Let's compute distances, a distance matrix comparing companies, and then group the companies. Or we could try to cluster the variables and look for groupings there. Let's do the variables, because sometimes you're interested in one, sometimes you're interested in the other, and just be aware you can do either one. The authors claim that it often happens when people do clustering on variables that they define distance as a correlation. So we have our N by P data. We have 8 quantitative variables, and we are going to cluster the variables. So I want, an 8 by 8 distance matrix for variable to variable similarities. And we're going to define similarity in terms of correlation. This is the sample correlation matrix for these data. For the 8 variables, sample correlation. Because I want to group the variables together in ways, where they're similar to each other. So let's define similarity in terms of positive correlation. Strong positive correlation. So what we can do with these numbers in order to really use them as a distance is, say, subtract them from 1. Suppose we subtracted that correlation matrix from 1. Now you have zeros on the diagonal, and small, numbers close to 0 indicate correlations that were close to positive 1. Numbers that are close to minus 2 or positive 2 indicate perfect negative correlation. Let me show you some R code for doing this. But for this data set, clustering the variables, we're going to use correlation as our measure of similarity, and we're going to get another dendrogram. Let me just show you the code. Let's see, actually I don't know if I have it here. So I'll just tell you how you do this, and then I'll show you next time, I think. In R, what I've seen people do, like if you look at the help file for the dist function, it has actually an example of using correlations as distances. And the way that they do it is they say as.dist 1 minus a correlation matrix divided by 2. 1 minus, and then the whole, that difference divided by 2. That would cause the numbers to go between 0 and 1. I don't know if that's strictly necessary or not, dividing by 2. It might just be to make it go between 0 and 1 and look nicer. I'm not sure. But I have some code that does it. Hierarchical clustering is very common. You will potentially get different answers depending on which type of linkage you choose. So I was going to show you some closing remarks. Remember, average linkage is same idea. It's just a different way of defining between cluster distances. And instead of the minimum pairwise distance or the maximum pairwise distance, it takes the average pairwise distance. So you can think of it as somewhere in between single linkage, which is most generous in calling things similar, somewhere in between that, and complete linkage, which is most conservative. Okay, so there are different methods for doing hierarchical clustering. What you might do, so there was a comment that I liked here. In terms of, which linkage method should you use? There's no perfect answer. So what you might do is do all of the 3 that we've seen: single linkage, complete linkage, and average linkage, and just verify, do they all kind of say the same thing? Hopefully it's not, I guess you would be more confident in drawing conclusions if regardless of how you looked at it, the same kinds of groupings came out. That's one thing that you can do. What else is interesting here? Be aware that with clustering, outlying values, with this hierarchical clustering where you're computing distances, outlying values can have big impacts. In fact, some of the more interesting dendrograms that you see are pointing at outliers. One individual is very different from everybody else, so it looks like an outlier. Okay, I think I will quit there. Next time we will talk about some more clustering techniques. You don't have to do hierarchical clustering. There's something called k-means clustering, which we'll talk about. There are model-based clustering methods where you say, maybe I think there's a mixture of 4 normal distributions, and that's a probability model for my data, and it's then just an estimation question. How do you estimate that model and do, by estimating the model, you basically do clustering, statistical models, based on statistical models. All right. So again, there's lots and lots of slides in here. I went ahead and LaTeX the whole thing just so I'd have it handy. And we'll pick out the pieces that I think are most important, which will be hierarchical clustering, which we've basically covered now. I want to talk about k-means clustering and non-hierarchical routines, briefly about probability models. and then we'll keep going from there. All right, questions about that stuff? And I'll see you next time. Thanks.